once again, hackers. Today we're pwning a program with the humble print function. Printf looks innocent. Compile a tiny C file, run it, and hello world comes out. But that output did not happen by magic. Something interpreted a recipe. Every language has a way to make numbers human. Print console.log system.out.println event that print then. Print. Our target is C's printf, the formatted output function. The word formatted is doing almost all the work here. The man page gives us the whole crime scene in one line. Printf runs chart format. One argument is the recipe. The dots are however many extra values that recipe asks for. Normal letters simply pass through. A % sign makes print4 stop being a typewriter and become an interpreter. %d prints a decimal. %x prints hexadecimal. %p prints an address-shaped value. %s follows a pointer and reads bytes until a null byte. %s follows a null byte. %t prints one character, double % prints a literal %, and widths such as %08x change padding. %2020 can add 20 printed characters while showing only one visible letter. Then %n does something different. It writes the printed character count through a pointer. First argument is special. Printf .cs input keeps inputs as data. Even the string %x, %x is printed literally. But printf arginput promotes the same user bytes into the recipe. The wrong person is now writing the recipe. The interpret starts asking for arguments the programmer never supplied. Our challenge starts with a global variable named sus equal to 0x21737573. It reads a word into buff, prints a fixed label safely, and then calls printf buff. Finally, it opens the wizard gate only if sus equals 0x67616C666. We do not need to smash the whole program. We only need to change exactly that value into exactly that value. The first number is not random. In memory, its bytes are 73, 75, 73, 21, SUS. The target integer looks like GAF when read left to right, but this is little endian. In memory, it becomes 66, 61, 67, FLAG. Our question is now mechanical. How can typed text write these bytes into sus? First we run normal input. Hello prints as hello, and sus stays unchanged. Then we probe with %p, 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 %p. A safe program would print those % signs literally. This target prints pointer-looking values instead. That confirms a format string vulnerability. The format recipe is working in argument shelf that was never intended to be exposed. The actual core is just printf buff. But after reading our %p tokens, printf behaves as if it saw printf, content, p, patent. arg1, arg2, arg3. It is not evil and it is not random. The recipe requests ingredients. The chef was never given them, so the machine reads from the places where arguments normally live. Pretend_f follows it. Pretend_m writes through it. Pretend_n writes through it. For control, we find where our input lands in that shelf. We place A, B, C, D, E, E, F, G, H, and try slots. At slot 14, the target returns 0x4847464544434241. Flip that little endian number into memory order and it spells A through H. So in this local run, argument 14 is the first controlled 8-byte block. Alignment padding is not the exploit. It makes the recipe exactly wine 8-byte ERES. Sus is global, so this local non-PIE target exposes it in .data at 0x404060. 2 bytes higher is 0x404062. We will write the high half 0x6761 to sus plus 2, then the low half 0x6761 to sus plus 2, then the low half 0x666 to sus. After the first write, the bytes begin to look like flag. After the second, they are exactly flagged. %n does not print the letter n. It takes a pointer and writes the number of characters printed so far. Printf, how a %n and count leaves count equal to 5. The h modifier makes %hn copy only the low 2 bytes. If our fake argument shelf contains the address of sus, the same feature becomes our controlled 2-byte write. One giant write would require more than 1.7 billion printed characters. That is ridiculous. Instead, split the target. 0x6761 is 26,465 and 0x66666 is 27,750. The first count is smaller and the second is only 285 more, so the counter moves naturally upward. The recipe is per second, 14 seconds, second retires, 9 tower time per second. 1,187 seconds, 2029 yay. First, a width field pumps the count to 0 times 6761. Slot 19 contains packed sus plus 2, so %h 50505. Slot 20 contains packed sus plus 2, so the second %a writes the height of 0505. Slot 20 compact sus, so the second %a writes the low half, the budge 5, the red act. What's a rest? During the final one, do not imagine 26,000 literal spaces on screen. Imagine a counter ribbon. It reaches 0x6761, writes at sus plus 2, grows by 1,285 and writes 0x6666 sus. The ordinary program then checks its variable pointer 67616666 and opens its own win branch. The flag takes 2x67616666 and opens its own win branch. The payload looks like wizard language, but the mechanism is boring. 1. User input controls the first printf argument. 2. Format tokens consume argument slots. 3. Our own bytes appear in those slots. 4. We place the address of source there. 5%hn writes the counter through that address. Recipes, slots, addresses, counts, writes. The fix is almost insulting in how small it is. Never let untrusted input become the format. Replace printf buffer with printf %s buffer. Feed it the same scary input. The machine reads one fixed %s socket, treats the full string as green data, prints it literally, and leaves sus unchanged. When solving these, sort specifiers by what they give you. %p and %x observe values. %s follows a pointer to read a string. If the address is valid, %n, %hn, and %hn and %hn write state. Leaks help us locate where to change what the program does. %n does not write a number typed inside the format string. It copies the number of characters printed so far. That is why the large widths exist. They are counter fuel. Keyboard bytes become a printf recipe. The recipe creates output. The output creates a counter. Then %hn copies the counter into memory. The dollar syntax makes this precise. Non-positional tokens walk one shelf slot after another. %19 Yoda's jumps directly to slot 19. %20 Yoda's jumps to slot 20. And because scan %24's buf stops at white space, we do not type literal spaces. Width specifiers make printf create them for us. Printf did not get hacked. It followed the recipe it was given. The bug was letting the user write that recipe. Safe code makes data become output. Unsafe code lets data become a recipe. Interpretation become memory access. And with %n, memory access become memory modification. Fix it with printf %s buff. See you in the next one, hackers. Before we leave, we play the exploit as a checklist you could use on the next format string challenge. First, read the source and find the call site. The dangerous shape is not merely a % in user input. It is user input becoming the first argument to printf. Second, run one harmless probe, a sequence such as %p.%ptoad, %p.tz whether the program is interpreting or interpreting. Third, put an 8-byte marker in the percent and positional slots. When the marker comes back as hexadecimal, you tell when you're on byte 63. Fourth, identify the state to actually need to change. In this target, that state is a global variable, source. The winning comparison asks for one precise integer, and the byte view reveals that the value spells flag in memory. Fifth, remember that %n does not magically write a number typed in the payload. It copies the number of output characters printed so far through a pointer. With specifiers as how we steer that counter. Positional specifier through a pointer. With specifiers are how we slate address. Packed but varieties are how when we stay for the write itself chooses size that makes the arithmetic boring. Two half-word writes are easier to reason about than one giant integer. Write the smaller half first, then add only the difference before the second write. Watch the byte roll after every operation. If the little endian bytes say FLAG, the integer comparison will see the value the branch expects. That method is useful because it replaces mystery with observations. Inspect the recipe, leak the shelf, find the marker, locate the target, count carefully, and write only what the challenge asks for, and the defensive lesson remains tiny. Keep the format string fixed. Pass untrusted input as data. When the program owns the recipe, printf is just output again.